Good afternoon, Professor.
Good
Good
afternoon.
afternoon.
Yes, I love it. It's like almost a competition, but not. Yes, good afternoon. Good. That's great. Good afternoon. I think that was Amy. I think that was either Amanda or Caitlin or maybe Christina. Good, but good afternoon. Good afternoon. That's awesome. And you're welcome to. I wish I. Okay, the new competition is, can I actually tell fast enough who's actually saying that? Because it requires looking careful. But hey, yes, awesome, awesome. Good afternoon. Thank you for saying so. And you just made my afternoon better. And wait, okay. So good afternoon, Amanda. Good afternoon, Caroline. Good afternoon, Christina. Good afternoon, Caitlin. Good afternoon, Savannah. Good afternoon, Samuel. Now I'm going to thank you. Good afternoon to you. Now, see, that's visual, just to be clear. Now I'm going to chat. Oh, by the way, you're also early. Thank you. Or you were. I mean, it was. Okay. Good afternoon, Amanda. Good afternoon, Alicia. Good afternoon, Kevin. Good afternoon, David P. Good afternoon, Caitlin. Hi, Christina. Good afternoon, Amy. Good afternoon, Chloe. Good afternoon, Felicia, and everyone. Oh, CC. Oh, that counts as multiplayer co-op. That counts as multiplayer co-op because she just acknowledged somebody in the room other than, anyway. Okay. Good afternoon, Savannah. And I still owe you all a lot, but it's coming back. You're getting things in dribbles and drabs. It's like a little bit scattershot what order things are coming in, but you're getting things. I have comments, but they're still coming. If you handed in something you haven't gotten back yet, that's me. That's not you. Okay. But that's all I'm going to say on that. On this, wait, there's more people here. Hold on. Sorry. Okay. Good afternoon, Savannah. Good afternoon, Adan. Good afternoon, Caroline. Good afternoon, Jamalette. Okay, I think that's okay. Oh, and in a moment, good afternoon, Elda. Did I say that? It's always so weird too. It's like if someone's on mute, that doesn't mean they can't hear me. I don't know what my problem. So, Elda. Oh, and there's more. Okay, sorry. Okay. Okay. We're going to start in a minute. We're going to get to some stuff, some more physics. Oh, and we have, wait, today's Wednesday. And just to be clear, so we're going to get rolling in a second. I didn't see you. Oh, and happy holidays to anybody that is relevant, or happy sweet new year to anybody to whom that is relevant. And of course, it is kind of a new year to all of us academically anyway. Oh, good afternoon, Elda. Sorry, good afternoon, Elda. Okay, cool. Wait, there was one other quick logistically, confirming. We're all under the impression that we all have. Oh, wait, someone's here. I'm sorry. Yes, they used to call me Dan Yaverbaum, the man who has not finished a sentence since 1977. Hold on. Okay, more people coming. So wait, while more people are coming, while we're getting set here, can you confirm or deny, any of you, in any fashion? We do have this class tomorrow. Yes, like tomorrow. Yes. Okay. Thank you. Oh, this totally counts as participation. Thank you. Okay. Well, awesome. Wow. God. That was it's almost enthusiastic, almost like we're excited to have class. Thank you, Felicia. Thank you, Amanda. Thank you, Don. Thank you, Kimberly. Thank you, Chloe. Thank you, Caroline. Thank you, Jamalette. Thank you, Nicholas. Thank you, Alicia. Thank you, Sophia. Oh my God. And thank you, Sophia and Amy. I mean, imagine if I'd said, I don't know what. All right, great. So we have class tomorrow. Great. Cool. So I'll see you all there. And by the way, so I appreciate those. If any, I do recognize a quick side on that. Like, I get that just because John Jay says that it's Monday or whatever, doesn't mean that your job in the Bronx is saying that it's Monday, or your child's daycare in Staten Island is saying it's Monday. Like, believe me, I understand that just because John Jay thinks they're pro Pope Gregory the 13th, that doesn't mean the rest of your life also agrees with that. So, long way of saying, whenever this happens, that John Jay declares a day on a day, of course, I'm going to hopefully be there and teach and all that. But and yes, we'll cover material and you're responsible for the material. But if you can't be there because there's another part of your life that didn't sign on to that, I totally get it. You don't have to like supply me with government documentation proving that. You just keep up with the material and watch the YouTube video or get the notes from a classmate and blah, blah, blah. But like, I get it. So those of you, if you can't be here tomorrow, I understand. And you don't have to like personally explain it to me. I mean, you can, but okay. Right. What Nicholas is saying. Right. So Thursday. So yes. And if that, okay. So yes, thank you, Nicholas. And thank you, everybody. So yes, I will be teaching tomorrow and I'll look forward to seeing everybody here. And there's no new homework due then or anything like that. Also, last thing on that, on the homework, as I just mentioned to people as they were coming in, like you're getting your stuff back in weird scattershot sequencing, like it's sort of coming, there's an order to it, but it has nothing to do with you personally or even the alphabet or anything. So just bear with, again, most of you are ahead of me. Most of you have turned in more than you've gotten back. And just to reinforce again, like I'm trying to catch up. I do apologize, but just know that that's good. The more, as long as you're ahead of me, then you're doing well in the class. And it doesn't mean that anything is lost or anything like that. And you can always just text me and say, I haven't got back in a while. Like, just want to make sure you actually got it or whatever. But it's all coming back and we'll keep talking. And there's no new homework due until a week from today. So we're still all sort of catching up with one another. I want to get, there's two very distinct equations on this front sheet here. One of which I've been alluding to for a while, the bottom one I've been alluding to for a while and writing in slightly different forms, but I haven't said anything about it yet. I want to get to it today, but also the top one I want to get to each of them is an aspect of velocity. Velocity is a very deep, I mean, in some ways, all of physics is kind of about the distinction between velocity and acceleration. There's a lot to say about both. So both of these equations are about velocity in different aspects, and we're going to hopefully get to them today. So that's what I'm going to do right now. So I'm going to change the view. So we're going to get going, blah, blah, blah. Okay. Oh, but right. Okay. So we're going to, basically what I'm going to, sorry. Oh, wait, I'm looking at direct chat. This actually, you may be right. No, good point. Thank you very much. And this totally counts. Oh, and someone else is here. Hang on. Or someone's having internet problems. Yes, direct chat. So, okay. Without names, someone in direct chat saying, I believe we don't have class next week, Wednesday. Will the homework still be due next week? Excellent point. You're right. We don't have class next Wednesday for a holiday. You are right. I'm getting confused keeping up with the schedule because the holidays are falling. Anyway, you're right. So I will probably readjust that homework assignment. No, in fact, no, I would definitely. And if you don't see a readjustment, because actually that's a very holy day for some people in this room and some people do like so of all the days in the world to assign homework like that is, and plus some people can't even eat. And when I say some people, I mean, actually that includes me. It's like some people can't even eat that day. I mean, they're not allowed to. So you're absolutely right. I'm sorry. That was a mistake. I don't mean to assign the homework for that day. I will adjust that. At worst, I might make it due. I might make it due a day that's not technically a class day, just because we have so many holidays right now, the way they're falling. I don't want to fall too far behind. So I might make it due that Friday or something instead of the next Monday. But yes, I will adjust that. Thank you, direct chat person. So again, to everybody, the homework right now looks like it's due a week from today. I will change that. And if you don't see a change in the next couple of days, or you can remind me tomorrow because we have class tomorrow. Okay, so I will change that and I won't make it earlier. Okay, thank you. Good point. Okay. Thank you. Oh, wait. Thank you. And direct chat person, that counts as closing the loop. Thank you for acknowledging my acknowledgement of your existence. Okay, so that counts. And yes, other direct chat person who has Zoom, internet issues, I totally get it. No problem. Thank you. Totally understandable. Last thing about the homework. So yes, again, I'm a little bit behind you guys. You are ahead of me, and that's always a good thing. And I'll tell you right now, if the semester ended right now and you were ahead of me, and stuff hadn't come back then that just is all the better for your grade. I mean, you can't get a bad grade if you're ahead of the class. So I don't want it to be like that. I want you to get your stuff back and you will, but as long as you're ahead of me, just don't have anxiety about, then that's a good thing. It doesn't reflect well on me, but it reflects well on you. And someone just reminded me, oh, but one thing about these homeworks, since now they are starting to come back more in, like some people have gotten homework 2 back now, some people have gotten homework 3, just so you know, it's a strange order. But even if you haven't gotten homework 2, I just want you to know, like some random people have gotten homework 3. So it is all kind of happening in weird ways. And one thing I'm noticing, everybody, I got to tell you, I notice this, what I'm about to say applies, it does not apply to homework 3, it does not apply to homework 3, but anything else, you've got to do the step method. I will, like, you have, even if I don't provide a diagram, you have to provide a diagram. In fact, honestly, if I don't provide a diagram, that's all the more reason you have to provide a diagram. I do in the early assignments to give you a model to show, but you've got to, the first thing you got to do for a problem is provide a diagram. And the second thing you've got to do is make the question explicit, the problem explicit. In fact, I've never said this before, but let me go an extra step and say, it might be a good idea for you to include a question mark. And I don't mean that sarcastically. Like right after you provide the fact pattern and the diagram of the problem, state the question, sure, in your words, sure, in an abbreviated or distilled fashion, sure. But make it, the point is to make it clear that that's the question. So whether you skip lines or underline or something, if there's any doubt that that's a question, put a question mark. Okay, I need to know what the question is before I start seeing how you're answering it. There's 1,000 reasons for that. And some of them ultimately have to do with actual real research habits that are crucial. Make the question clear. Then go to step 3, which is general definitions and principles. Statements that are true, independent of the question. Then step 4, start applying those general definitions and principles to the question. And then finally answer it. By answering it, that means you're going to have something that's circled that is a complete thought that clearly, explicitly ties back to your step 2, which was the question. The whole thing is like a complete, ideally a homework problem would stand on its own as an independent, self-sufficient, small, complete physics proof of something. Like if that makes it, like it should stand on it. So it presents a scenario, asks a question about the scenario and answers it. It's like a little paper or a little poster, even if it's very little. Okay, so please, so I am noticing, I mean, to be like my one little suggestion for improvement to everybody is, I like by homework, like of course you didn't know any of that when we did homework 1. And again, also, whenever you get any of these grades back, even if they come back later than you can always revise them. We haven't set any kind of hammer down deadline or anything yet. Anything you've done or anything you were supposed to do can still be done. And anything you've done less than perfectly can still be revised to perfection. But in homework 1, we understood that you didn't know what you were, but by homework 2, I think we had the 5-step method. Like you want to do the 5-step method at all times. Okay, enough on that. Now let's go on. There's 2 equations on the sheet. They're different. They're about something, they're about velocity, but they're different equations and they're kind of on different topics. I want to go, so the first equation says, I'm going to explain it now. I'm going to back up and explain it, but it says GPR form number 4. And then it has a bunch of symbols. Someone's here. Sorry. So this first thing that I'm now going to talk about, this first equation on the sheet, GPR form number 4, what that means is the 4th form of Galileo's principle of relativity. Okay, the 4th form of Galileo's principle of relativity. So I'm going to so where this is coming from in the first place is the train of thought assignment, homework number 3. So I'm about to turn the page on this, but I'm going to back up and refresh us on like the big conclusion that kind of dropped right at the end of our spectacular discussion last Wednesday. So I'm going to turn the page here, but I'm turning my thoughts to homework number 3, train of thought. And I'm going to remind you now and write down for you, and please write this again, even if you've already written it once. I'm going to write down for you and say again, what Galileo's principle of relativity is, in its first three forms. Okay, in theory, that's what came out of last time, but I'm going to do it a little bit more slowly now. And then those three forms build ultimately or lead to a fourth form, which is written right here. And there's 5 more forms that are going to come over the semester. I mean, so here we go. Okay, so backing up again, we did this whole train of thought discussion. We were like in a train, but there was like no signs of motion because it was so smooth. So we were trying to figure out, is it moving or not? And can we like look up at like any white lights that are going by and use that information to figure out whether it's moving? Like first, there's no information at all. We're just in this train. It's totally smooth, but we know trains have the potential to move. And it's like, but it's dark, so we can't tell if we're moving or not. Then we like look, then we get more information. We see these white lights and they're all moving past us, but they're moving past us in formation. Like they're all like, there's some pattern of white lights, but the pattern remains steady and they all move past us as that pattern. So it seems like more information. It is more information, but we say to ourselves, well, it's more information, but it's not clear that it locks down the question because like, all right, all these white lights are moving now. So that seems to indicate that we're moving. I mean, like we're not in the same place in relation to the white lights. But then we also think about it and we're like, well, all the white lights are like moving together. So, I mean, it could be that those white lights, like those could be the white lights of a station that we're moving through, or those could be the white lights of like another train that's passing us. The fact that all the white lights are moving together like suggests both possibilities sort of almost with equal persuasiveness. Like on the one hand, like if they're all moving together, that really could be like one big object, like a train could be moving past us. On the other hand, if they're all moving together, that's sort of a weird coincidence. Like, why would they all be moving together unless it was a train? So doesn't that suggest that maybe it's an easier explanation that we're moving past them? blah, 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 blah. And what I said at the end of our discussion last time is all this is a big analogy to what literally was happening in history for hundreds and thousands of years as human beings thinking, reasoning, curious, well, some curious, some not, but certainly observant and analytical human beings would look down at the ground below their feet and see no evidence of motion whatsoever, i.e. their feet are not slipping on the ground, our feet are not slipping on the ground is stable. Furthermore, let me go a step further, say you drop a rock from your hand, from nearby your shoulder, you drop a rock onto the ground. It lands on the ground directly below wherever you dropped it from. In other words, it doesn't land like over there behind you or something like that, or it doesn't like lurch forward. Like there's no, everything you do seems to indicate relative to the ground that the ground is still. But then you look up, you as any member of any person in any stage of history, like ever, you look up. And in the morning, you see the sun rise in the east and it goes across the sky and then it sets in the west. And then maybe you think to yourself, okay, so the sun is moving past me. Like, that's interesting. I wonder how the sun does that. But that's what you think. Then you see the moon doing the same thing night after rising in the east, setting in the west. And you think, okay, fine, the moon's. But then you see all these all these white lights that all go across the sky every night. Like you might, I don't know if you've noticed this, but if you ever look, you will notice that stars don't just appear. They don't just sit there. They all go across the sky in the manner of the sun and the moon. They go across from east to west in a big formation, like in groups of stars known as constellations, in shapes that people have been recognizing for centuries and millennia as certain shapes, like whatever your birth, like the 12 signs of the zodiac, or the 12 constellations of the zodiac, for example. You may say if you're born in September and you know that you're Virgo, right? Virgo. Yeah, like I think if you're born in September before the 22nd, I mean, if you're born before the 22nd and you know you're a Virgo, or you're born after the 22nd, you're born in October and you know that you're a Libra, right? That's supposed to mean, like, Libra means that there's like a bunch of stars in the sky that supposedly is shaped like two scales. Now you may say to yourself, well, people are pointing those things out to me and I don't think they look like scales at all. I think that's nonsense. Fine. You may not think they look like scales. You may think they look like a paramecium. But the point is this: when someone says, don't those look like scales? And you go, no, it looks like a paramecium. You both know what you're talking about. There is definitely a formation of stars there that you can call whatever you want, but the stars are in a certain shape. And that shape does not change from hour to hour or from night to night or from century to century. Or the same thing with the Big Dipper or Orion's belt or anything you've ever recognized in the sky. I don't care what you think it looks. I mean, I do. I care very much. Like I do. But I don't care what I think it looks like. The point is, there's an it there. There's a shape of stars that's not changing. What's my point? My point is that all the stars are moving together. They're all staying in a certain formation relative to one another. So night after night, there's like, if you were to look up with your naked eye and you didn't live smack dab in the middle of like light polluted New York City, you would see up to like 1,500 points of illumination in the sky that are all in a formation, like the canopy of stars, so to speak, they call it. And they're all moving together night after night after night. So it raises the question, wait a second, that's kind of really like 1,500 like illuminated objects are all sticking together and all moving through the universe while we just sit here and watch it. Well, that certainly would be, I mean, that certainly could be, but that seems kind of like an extraordinary coincidence that we would be sitting still while all these other things are moving together. And I don't want to, so there's a deep question that it's like contemplated for years and years and years. And I mean contemplated. I mean, both sides are considered by different groups of people. Like, it's not like Copernicus or Galileo or Columbus, for heaven's sakes, are the first people that ever thought, I wonder if the earth is moving. Like, no, This was wondered for a long time, but the point is, it's wondered. It's very hard to resolve. It's very hard to resolve, or to a point, it was very hard to resolve whether the Earth has velocity or not. Basically, because if you look down, it seems like it doesn't. And if you look up, it seems like it might. And when you really think about, so what's the resolution of this? Galileo comes along after Copernicus showed a way that we could, after people did present ways where we could look at the universe as having an Earth that's not at the center and not sitting still, but rather moving past, say, the sun. Like, people presented this idea. Aristarchus presented this idea like in Greek times, like what didn't catch on, but people thought about it. And then Copernicus presented it in a much, much more detailed, much more persuasive mathematical fashion in the 1500s. It still didn't really catch on. And also he was smart enough to present it as a mathematical model, not as actually a physical reality. But finally we get to Galileo, who's in 1632. And if I'm not careful, as you can see, I could already get myself way off. I love Galileo. There's a lot to say about him. But Galileo, well, the big breakthrough of Galileo that distinguished him from many of his predecessors, well, number one big thing is he made a telescope and started looking through the telescope and looking up at the sky and drawing what he saw. Now, a couple of people had telescopes before him, but only a couple. Like, it was invented in his lifetime, and the few people that not by him, but the few people that did invent the telescope in his lifetime, they didn't use it to look up in the sky and draw what they saw. That was his adaptation or his adoption of the telescope. So he started seeing things, and if you're ever more curious about this, text me private. I can recommend books and so forth about it to you. But Galileo started drawing what he saw in the sky and started thinking about it in a whole new way. He got closer to the sky by 4 to 10 times. He could magnify the sky and bring it closer to him by 4 to 10 times closer than any human being had ever done before in the history of civilization. And he knew it. And he was drawing and taking in the data studiously night after night. And so he started really taking seriously the idea that the Earth could be moving, but he still had to grapple with the problem that it certainly doesn't feel like it's moving, and it certainly doesn't look like it's moving if you look down, and it certainly doesn't do any of the things to you or make you do any of the things that you're used to thinking that you do when you in fact are moving. So what's the deal? Galileo realized, so Galileo developed something called a principle of relativity. A principle is something that comes even before laws. It's something that tells you how the laws are going to unfold. Galileo, in order to resolve how it could possibly be that the Earth could possibly be moving without us feeling it or without us having any evidence of it, Galileo backed up and said, well, hang on a second. Here's the thing. I can't necessarily force you to believe that the Earth is moving, but I can raise this point, which is if you were in a boat, he said this. This is not what's written on the page. I'm telling you, in one of his books, called Dialogue on the Two Chief World Systems, he presented a scenario very much like the train of thought scenario. They didn't have trains then, but they had boats. And he said, look, imagine if you go down into a boat while the boat is docked, before the boat leaves, and you go down into the chambers of the boat, the bowels of the boat, and you arrange your little cabin. And in your cabin, you have like a table and you have a chair and you have your books and you have like a fish bowl. You literally, like you have a bowl with like a fish in it or something. And you like take observations as rigorously as you want of what's going on in that room and on the desk and in the bowl with the fish before the boat leaves the dock. And you look at the way everything is, and it's all stationary, and the fish is going round and round with no problem. And if you drop a ball in that room, it's going to land directly below your hand next to your feet. Make a bunch of observations. Now, after you've done that, let the boat leave the dock and let it start cruising on the oceans, but in a steady, constant velocity, like constant speed, constant direction kind of way. Just let the boat be as steady as it can. Imagine it's a very big boat, so it can handle the waves and stuff like that. It doesn't experience much of the waving. Once that boat is going and has achieved cruising velocity, you're down in the cabin. Take observations again in your cabin. What will you notice? What will you notice? You'll notice the same stuff that you noticed when the boat was docked. This is Galileo talking in like the mid 17th century in a book. He's saying to people like, look, wouldn't you feel basically all the same things in the boat once it's moving as you did when it wasn't moving? Which is sort of what you guys were discussing last week. Like if you were in a train that was smooth enough, maybe not a New York City train on a bad day, but maybe a Tokyo train on a good day, or a Washington, D.C. train on a good day, or maybe a John Day elevator on any day, right? If you get in a vehicle that's moving smoothly enough, it totally feels as though it's not moving. And if you're in a non-moving vehicle, it feels like it is moving smoothly. Why? Galileo says because, and here it is now. I know I've spent a long time going around the mulberry bush here, but look at the board in the black. What Galileo is saying is here's a principle. The principle of relativity is that whatever the laws of physics are, maybe we know some already, maybe we don't, maybe we're going to know a lot more in future generations and future centuries, but whatever the laws of physics, laws of motion, the laws of motion through space and time, whatever those laws are, they're not going to change from one velocity to the next. They're the laws that govern velocity, acceleration, position, whatever these laws are. They're not going to change from one velocity to another, just like laws of the land don't change from one circumstance to another. They don't apply one way to me and differently to you. Or if you can't steal, if that's a law that you can't steal, then it's not like you can't steal from your neighbor, but you can steal from your cousin. Like, no, if it's a law, then it's a law. And if it's a law that governs how speed works or or acceleration works or how force works, then we're not going to change the law by changing our speed. So Galileo says whatever the laws of physics are, they're going to be the same at 0 miles an hour going to the north as they are at 15 miles an hour going to the east. They're going to be the same at all. Hold it all. Oh, sorry. Oh my God. That says at all context velocities. That's supposed to say constant velocities. I'm so sorry. At all constant velocities. The laws are the same at all constant velocities, or an even fancier way to say this, really a slightly more proper way to say it, and not that he wasn't writing in English anyway, but a slightly more proper way to say it is the way right below, that the laws of physics hold in all inertial reference frames. Now, I want you to make a note in your notes, please, if you're still with me, if you're still paying attention, because this is a more proper and more instructive way to say it ultimately. It basically means at all constant velocities. But to be more specific, inertial, the word inertial, like make an asterisk or make a sidebar in your notes, please. The definition of inertial is unaccelerated. That's all it is. Inertial means unaccelerated, meaning not changing its speed nor direction. That's what inertial means. Okay. And a reference frame, please put in your notes or define separately. A reference frame is a perspective maintained by an observer assumed to be stationary. Okay, I'll say that one more time. A reference frame is a perspective held by an observer assumed, or you could say hypothesized, or you could say posited, asserted, but an observer assumed to be stationary, to be at rest, to be still. Okay, we're going to expand on that more and more as we go on in the class, but a reference frame, in fact, one more thing too, reference frame, when I said it's perspective, what do I mean by a perspective, you might ask? Well, a perspective is a way of looking at things, but specifically in physics, a perspective, so maybe put this now as a third definition. So we've defined inertial, We've defined reference frame. Now I'm defining and a reference frame we've defined as a perspective held by someone at rest. But what do I mean by a perspective? I really mean a coordinate system, like a coordinate system for measuring, for taking measurements of position, velocity, acceleration, taking space-time measurements. So a reference frame is a perspective. A perspective is a coordinate system. Now, all of this, so we'll talk more and more about, sorry. Yes, thank you. I'm so glad that someone's paying attention. I'm glad you are paying attention. Yes, absolutely. Thank you. And that is total point. And I'll even say, I'm even going to say, and I do need to make more portals on this. I say Elda gets, also can submit this for multiplayer co-op because she went public with it. Thank you. Like, so it could benefit everybody. And I appreciate the guys. So yes, the definition of inertial is unaccelerated, not accelerated, which means constant velocity. Inertial means not changing speed nor direction. That's what inertial means. Not changing speed nor direction. So hopefully that's good. And you can tell me if I should do it again, or anybody can tell me, or even if someone else. And again, even if Elda just cued someone else into realizing, like, oh, something's going on in class now, like they're actually writing things down. Oh my God, I was like totally feeding the dog or something. Then someone else could still say now, oh, I'm sorry. Could you also repeat the other day? Like, don't be afraid to admit, you get my point. All right, so thank you, Elda. So what I'm summarizing, what I'm saying, this is the first way, this is form number one. This is form number one, like kind of the earliest way or the most fundamental way that Galileo like wrote or said the principle of relativity. I mean, he didn't write it in English. He originally wrote it in Latin and in Italian, and then he wrote it in Latin, and vice versa. But what I'm saying right now is this first form number one, and I'm going to give you 3 more today, even if we get to nothing else. I'm looking at the time. Yeah, you're going to get 3. But this form is saying whatever the laws are of physics, whatever they are, they're not going to change from one speed or direction to the next. For example, I don't know what the law of gravity is exactly. I mean, like none of us exactly know. Galileo didn't know exactly what the law of gravity was. And you guys in the class might know something about gravity, but not like all the math or something like that. But we all know at a basic level, something about that there's a law of gravity. We all know that if I drop something, if I release something, if I stop holding it, it's going to fall straight down. We just know that from experience. I mean, I don't think anybody would dispute that. So let's just call that a law. So that seems to be some sort of like descriptive, universal, earthly truth that things fall. Like what goes up must come down. Okay, consider that a lot. And specifically, what goes up comes down, like straight down, right? So take that as an example of a law in your head. It doesn't matter if we know all the math or all the details of it, neither did Galileo. But if we believe that things fall straight down, what Galileo is saying is that's true, regardless of what speed we're going. Like if it's a law, it's a law. It doesn't change. Like Earth doesn't know what speed I'm going. So if I drop a pen, it drops due to Earth, regardless of what speed I'm going. That's what he's saying in form number one. So what's that got to do? Oh, and by the way, he's on purpose. It's a principle that comes before laws. We're not assuming that we know all the laws. We're assuming that there are some laws that we're going to figure out. But the reason this is a principle is because it seems almost self-evident. It seems very hard to argue. If you're following what I'm saying, especially with the help of Elda, who got us to repeat the definition, if you're following what I'm saying, hopefully what you might be thinking is something like, okay, I get it. I mean, I think I get what he's saying. It doesn't even seem that hard what he's saying. He's saying the laws are the same at all speeds. Like, I get it, but that seems so dumb or so obvious. Like, I don't even see what the point is. Like, so what? Like, I knew that. Like, why do I need a physics class for that? If you're thinking anything like, duh, then you get it. You're with me so far. If you think that law this principle not only makes sense, but makes so much sense that it seems like almost not even worth saying, then you're with me, because this is the point. And all great physics always works this way. We're saying something that we think you should totally agree. Like, we don't think we're ramming something down your throat that's new. We just think you've known it so much your whole life that you would never necessarily know that it's important. This is what makes what makes this interesting, is that it turns out, if you just seize on this truth for a moment, it turns out to actually bear fruit and mean something. How? What? So hopefully, in other words, so I'm not proving this. I'm appealing. I'm saying I think this is somewhere self-evident. It's a principle. But now let's look at form number 2. Form number 2, like, in other words, a next other way of saying the same thing, or an implication. I'll say this. Okay, now, and again, let me remind you, I know I wrote these things quickly at the end of last class, and you did too. And I know I blasted through and said something about them, but I'm telling you, this is so, I'm aware of that. But please don't view this as a waste of your time. Well, view it any way you want, but please write them down again, just like I am. And you'll notice the words are maybe slightly different, but hopefully, which shows you there's a little flexibility in these wordings, because again, he didn't write in English in the first place. But there's also something very not flexible about these wordings, because we're getting at like a very real idea here. So here's form number 2 now. And I'm saying it's not a different law. It's not a different law. It's not law number 2. It's not principle number 2 or anything like that. It's a different form, a different way of saying, a different implication or consequence of the first thing we said. So this is form number 2 of still the same principle. The principle is that the laws of physics, whatever they're going to be, and this is whatever they're going to be, we have a whole still class, semester to continue through, and then another semester, whatever the laws are going to be, this is how they're going to work, is what form number 1 said. And if they're going to work the same at all velocities, which again is what form number 1 said, like, or to take Elda's point, like, they're going to work the same at all constant velocities. Like, as long as I don't care whether you're going 100 miles an hour to the east or you're going 4,000 miles an hour to the west, as long as whatever you're doing is staying the same, as long as you're going at a smooth, unchanging speed and direction, i.e. velocity, i.e. as long as you are inertial, as Elda asked, as long as you are inertial, not accelerated, then the laws are going to be whatever the laws are. So then form number 2 says, oh, wait a minute. If that's true, I mean, if we really believe that, and I think we do, because it almost seems like, duh, it seems like obvious, laws are laws. If laws are laws, then what form number 2 says, well, then that seems to mean that you can't do an experiment. You couldn't do any experiment. You can't even think of, you can't even design an experiment that would measure, that would quantify, that would observe, quantify, detect the velocity of a single object. Now, whoa, wait, isn't all of physics all about velocity? Yes. And isn't physics all about experiments? Yes, at least since at Galileo it is. So what the heck are we saying? We're not saying there's no such thing as velocity. We're not saying there's no such thing as motion. What we're saying is you could never in an experiment measure the absolute velocity of a single object. Oh, wait, I'm just looking at. Okay, of a single object. Now, let me be very careful here. And you might want to, I mean, this is a huge idea. It's really a big idea, but it's no bigger than it is. Don't make it too big. So you may want to put in your notes. So you see how I have the word absolute in quotation marks and in parentheses. I don't want to like ruin this page, but please in your notes, make a note somewhere that says absolute does not equal, like triple equal sign slash through it. Absolute does not equal actual. Or real or something. I'm not saying there's no such real thing as velocity. I'm not saying you can never measure velocity. I'm saying you can't measure in an experiment the velocity of a single object, of an object by itself, of one object just in and of itself. You can't do an experiment to know how fast something or what direction something is going in space by itself. In other words, you can't know in an experiment whether the train is actually moving past the platform or the platform is actually moving past the train. You can certainly know that they both are doing something different. Like you could see the white lights. You can know that something is happening, and you can even measure that number, that the white lights are moving 50 miles an hour faster than the train, or the train is moving 50 miles an hour slower than the white lights to the east, or maybe the train is moving 50 miles an hour faster than the white lights to the west. Like, I'm not saying you can't get numbers, but I'm saying all you can know is a comparison between the two in an experiment. You can't know what one thing is absolutely doing compared to space. Let me be finally more specific. Like, in other words, say you're in an airplane now. Like, airplanes are a little bit more smooth than a lot of subways that we're used to. Say you're in an airplane, you're on like a long flight, transcontinental flight, and you've like fallen asleep on the airplane, which is also, by the way, quite realistic, right? People fall asleep on airplanes all the time. And it's like so long flights in the middle of the night, So you wake up. Or wait, is it? Yeah, like you wake up and it's dark and it's so you don't know it, or even, okay, not to be like this. I fly every week, okay, and a lot of times like we'll get in the plane and we're getting all ready and everything, and I fall asleep, but like they haven't taken off yet, and there's like delays and stuff, and then I wake up and I literally don't know, have we taken off yet or not? Like that totally, and it's not just because I'm crazy, even if I am, like that can happen. And maybe it's dark out, so like there's nothing I can tell from the window. So say, sorry. Yeah, I'm totally gonna look in the chat. This is good. Whatever's in the chat is good. Yes, okay, that's really good. And by the way, he went public. Thank you so much. And total points. So Sam went. It's like saying you can't know what's good until you know what's bad. Yes, all what I'm saying is very much like that. There's only one catch. Is that yes, it is very much like that. Except I'm talking about science. I mean, not to diminish that, but just to be clear, I'm saying something like that. But often that's like a figurative point or an emotional point. I mean, it's a very true point what Sam is saying. But I just want to say that that even applies to strict, like numerical measurements in the actual physical world. Like even in a realm that you might have thought was stricter or more absolute than that, I'm saying yes, even velocity is like that. Like, yes, if what Sam Ajayo is saying, if he's saying like, am I saying, so you can't really know about velocity unless you have a comparison? Yes, I'm totally saying that. And I'm saying it in a very, very real way. Like, yes, totally. Let me be specific for a second. If I wake up in that airplane and I'm like, wait, I don't know if I'm moving or not. Or even, let's even say like I look outside, maybe it's even daytime and I look outside and I even see clouds moving past the window. So I see clouds moving past the window, but I say to myself for a minute, wait, okay, they're clouds moving. So that tells me something. But then I go, hold on. Do I know what? So I see the clouds moving, but is it that the plane is moving past the clouds? Is it that the clouds are actually sitting still and the plane is actually moving past them? Or is it that the plane is actually sitting still and the clouds are actually moving past it? I asked myself that. So here's the kicker now. And yes, Sam is totally with me. Hopefully a lot of people are with me. But now here's the real kicker. Like, let's say I don't just want to be in my head. I don't just want to think about things like, oh, I guess it's like good or bad or taste or like these emotional things that can sort of maybe never be resolved fully. Maybe I say to myself, no, by God, I'm a scientist. Like, let me be like scientific about this. Like, stop the nonsense. Like, come on. Let me, like, I'm in a modern world. I've got like equipment and like rational thoughts. So let me do an experiment, I say. So here's the kicker now. Let's say I say to myself, I'm going to do a freaking experiment to actually like get rid of my mystery and actually figure out what's actually going on. So I decide to do an experiment. Let me, and I got to do one that I understand. So maybe I start with a very simple experiment. Like I'd say to myself, okay, I know certain scientific laws that I can rely on, like gravity. I'm going to drop something from my hand. I'm sitting in my seat. I'm going to take a bag of pretzels. I'm going to drop the pretzels from my hand and I'm going to watch them and see what they do. Maybe I'll even time them. Maybe I'll get out all kinds of apparatus and I'm going to watch these pretzels fall because I'll tell you why I'll do that. Because I know what the pretzels would do if I were actually standing in a parking lot. If I were actually, as far as I know, if I were actually at rest, stationary in a stationary reference frame, in a parking lot, or in controlled conditions in a freaking lab, and I drop pretzels, I know enough about the law of gravity to know they would land on the floor directly below my hand. Like they would fall vertically straight down. And maybe I even know enough to know from high school or something like how much time it should take for them to fall or something like that. So I would like set up the whole deal and I would drop these pretzels. So I would start to do an experiment to find out whether I'm actually sitting still in this airplane or I'm actually going past the clouds. And here's the problem. The problem is form number one that we just said a minute ago. And maybe I'm going to pause for a second. Maybe someone could tell me in the chat or with voice. Like, I'm guaranteeing you, I know what those pretzels would do if I were standing in a parking lot. They would land directly below my hand. So I could set up this experiment and say, as long as they fall directly below my hand, as long as they land on a line directly below my hand, then that'll show that I'm actually sitting still. Like that's what I could say, like experiment, hypothesis, procedure. There's my hypothesis. As long as the pretzels land, and again, you can be more specific if you want. You can say, as long as they land in 1.3 seconds or like whatever it's supposed to be, then boom. Since I know that's what would happen in a parking lot, boom, that shows that I'm parked. But actually, but what's the problem with that? Why is that experiment doomed to failure? Like, why is that experiment actually not going to reveal anything to me? I'm asking you now, so I'm going to pause for a second. Anybody who wants in the chat or with voice or with video or whatever, look at form number one and tell me why actually, no matter how well designed or how knowledgeable I am, no tricks up my sleeve, why is that experiment not actually going to reveal squat to me? I'm going to pause and I'll say the question. And by the way, I am going to pause. I want some kind of answer from someone or some kind of input. This would be an opportunity. If suddenly you're like, oh, wait, he's asking us something. Whoa, put down the dog. Like you could put in the chat, wait, what was the question again? Like don't be embarrassed. Like I get it if you've just tuned in, but I am now asking a question. I want to know, why would such an experiment, like dropping something, why would it not be able to resolve the question for me, whether I'm moving or not? And here's a hint again, even if I know what would happen if I weren't moving, it would land directly below me. I know what would happen if I weren't moving. So why can't I do this thing? Why can't I drop something and say, so if it lands directly below me, that means I'm not moving, because I know what would happen if I were. Like, why can an experiment not resolve the issue of whether I'm actually or moving or not? And it's based on form number one. So again, I'm going to pause. I'm going to change the view here. I'm going to pause. And if you want me to repeat the question, Or, okay, I'm going to ask this. Can you just do an electronic hand if you hear that a question is being asked? You don't have to, cool. Thank you, Amanda. Thank you, Elisa. Thank you, Jamalette. Thank you, David. Thank you, Amy. Thank you, Caroline. Thank you, Kevin. Thank you, Elisa. Thank you, Chloe. Thank you, Christina. Thank you, Caitlin. Thank you, Samuel. Thank you, Kimberly. Thank you, Nicholas. Awesome. Okay, great. So I'm taking enough people. So now I'm not going to force anybody, but could anybody want to take a stab? Thank you, Savannah. There's other people too. Sorry, I have a weird view on my screen, but okay. Thank you all for raising your hand. So does anybody, Sam, is that a volunteer for an answer, or you're just saying that you do know the question?
I know the question.
Okay. So does anybody want to, and my big hint is look back at form number 1. Like, and again, I'm saying, we know what would happen if we were stationary. So what's a problem with, if we know how the experiment would turn out if we were stationary, why can't we do an experiment, see how it turns out, and then go, oh, if it turns out that certain way, then we were stationary, then we're actually moving at 0. Like, why does that not actually, and it is the same thing as train of thought and everything else. Why does that not work? Look and see if anybody. I'll give one more hint, or I'll help along. Here's the thing. Okay, and again, this is just an example of an experiment. The example is that I drop something and I drop it in order to find out. So I'm trying to find out my actual velocity, my absolute velocity through space. What I'm really trying to find out is it 0 or not? Like, that's what I can't tell. It's either 0 or some number. Like, I can't tell. I know that my velocity, like, past the clouds is something, or the clouds past me is something. I know there is motion of the clouds compared to me, or there's motion of me compared to the clouds. But what I'm trying to figure out is, am I absolutely moving or not? And so I do this experiment, I drop this thing, and I figure to myself, hey, I know what would happen if I weren't moving. The object would land directly below where I dropped it. So if I were to drop it and it were to land directly below where I dropped it, that would mean I'm not moving. Like, that's my idea. But I'm saying that if you really take form number 1 of this principle seriously, you'll see that that idea doesn't work. And my hint of why it doesn't work is, let me ask you this, because I'm still throwing it out to you guys. I'm not like, well, we have that. Wait, Caroline, awesome, Caroline. Whatever you're saying is awesome. Let me see. That's a really good, okay, so Caroline's asking, she's putting in the issue of direction, which is great that she's putting in, and I think I understand that. So she's saying, does the direction matter, whether the object is going up or down or even left or right for the velocity? So direction does matter for the concept of velocity. Yes, like velocity means, so great question. It's a great question, period. It's possible that I'm misunderstanding it, so you can clarify in a second, but I think I understand it. But even if I'm misunderstanding, it's still a great question. Yes, for when we're talking about the velocity of something, we mean the speed and the direction. So like going left is a different velocity from going right. That's definitely the case. Like 30 miles an hour to the left is a different velocity from 30 miles an hour to the right. So yeah. Now I'm saying, if I want to know what I'm doing, if I want to know whether I'm going in a certain direction or a certain speed, or if I'm not going at all, if I want to know whether there's a number at all or whether the number's 0, like I might drop something. And dropping, again, to everybody, dropping is just an example of a very simple experiment where we would pretty much be confident that we would pretty much think we would know how the experiment should turn out under certain conditions. Like it could be, if you don't, okay, I'm looking. Good, I'm seeing something in the direct chat. In the direct chat, I'm seeing something that's very good. It's very good. Yeah, I'm questioning whether I should read it out loud or not because it's in the direct chat. But yes, I see something in direct chat that's very good.
You can.
Oh, okay, thank you. Okay, well, all right. So it says in the direct chat, you can't measure the absolute velocity of a single object against space because that single object would be its own reference frame, question mark. Right, and that is what I'm trying to say to everybody, like what he just said, and I might say it again, I am trying to say, or what he or she just said, I'm just trying to flesh it out in even slightly more concrete terms. Like, or really what I'm asking is, why is that? Why can't we? I mean, yes, it seems like the law is saying that we can't, but relate it back to form number one. Okay, cool. Thank you, Caroline. Awesome. Okay. Relate this back to form number one. Like, here we go. Okay.
Put it
Cool.
in the chat. Everyone see.
Yeah. Cool. Oh, wait, sorry. Talk. I'm sorry. Say, Sam. What? Say.
We're just putting it in the chat for everyone to see.
Yes, thank you, and I appreciate that. And it's good. And what Caroline and guys, also, I'm noticing a slight trend that many of us are getting moving gingerly from private to public. I think that's great. You're still always allowed to do the private because I totally understand, but I'm taking it as a good sign. The more we're feeling confident to go into the public chat, I really think that is the better for everybody, honestly. And I hopefully that sends a message more and more to all of us that it's like, okay, even if you say something in the public that you don't think that I think is perfect or something, like whatever. But slight sidebar on that. Notice, even though we're just sitting here talking, even though you don't like see numbers, or even though we don't have rulers and stopwatches with us, we're talking about experiments here. And what we're doing is experimentally talking. Science is all about experimentation, even when there isn't equipment. It's all about messing around, fooling around, playing in the sandbox and just trying to sort things out. And knowing that 90% of what we do in the lab or in a discussion or in a homework assignment or anywhere, 90% of what we do in physics is rough drafts. It's just brainstorming. It's just kicking around stuff. And then every now and again, something will gel onto something that seems mind-blowing. But we're just trying to play until we have a couple of occasionally mind-blowing moments. We don't have to be blowing our minds every more. So I mean, the more that everybody's comfortable playing in the chat and thinking of the chat is just one big social or intellectual experiment, all the better. I mean, so awesome. So let me say what we're trying to do right now with Sam's comments in the chat and with Caroline's comments in the chat. What I'm sort of asking us to see is like, how is it that we could get from form number one, which says the laws are always the same, like duh, they're laws. The laws are always the same. And then form number two says, yeah, but therefore, if that's true, you're stymied in experiments. And experiments are what it's all about. If we can't figure out something in experiment, then we're not doing science. But form number two says you ain't never going to do an experiment that's going to tell you whether you're actually moving or not. And the reason is that, and what I'm looking for us to fill in is like, why? Why can we never do an experiment? Why, in other words, why is train of thought not just an abstract hypothetical? Train of thought is the real deal. Like any confusion that you've ever had for a moment on a train or in a car or in an elevator or in an airplane, if for one moment you were confused as to whether you actually are moving or not, when you then moved and resolved that confusion and you're like, oh, I'm an idiot. Oh, I totally am moving. Okay. For a second, I didn't know whether I was actually moving or not. But oh, then I figured it out. I'm actually moving. Oh yeah, I'm in an elevator. I'm actually going to the fourth floor. It's not like the fourth floor is being brought to me. Surprise, surprise. When you said that to yourself and you got that clarity, you said, oh, actually, the real deal is like, actually, I'm moving and the fourth floor is not. Guess what? I'm here to say, no, actually, you just confused yourself again. When you were openly confused, in the one moment when you actually didn't know what was going on and you actually didn't know whether you were actually moving through space or the fourth floor of the building was actually moving, that's when you were more correct. That's what Galileo's saying. And here's why. Because any experiment that you would do to actually resolve it or to convince yourself of what's actually going on, any experiment you would do is BS, because it's going to work out the same way, whether you're moving or not, Because of form one. In other words, form one says the laws are the laws no matter what. Gravity is gravity no matter what. It doesn't matter whether you know all the math of gravity or not. You know what gravity is. Crap falls straight down below your hand, right? And form one is saying that's going to happen at 0 miles an hour or 100 miles an hour or 300 miles an hour. And guess what? That's why you freaking feel the same, whether you're at 0 miles an hour or 100. The reason when you're in an elevator and you've lifted off and now you're cruising, like you're leaving from the first floor and you're on your way to the 13th floor or whatever of John Jay, as in the middle of that journey, when you're cruising past the 4th floor and the 5th floor and the 6th floor, the reason you could close your eyes and feel nothing is because there's nothing to feel. Is because if you reached out your hand at that moment and dropped something, of course, it would land directly on the floor, directly below you in the exact same amount of time as it would if the elevator were sitting still. The laws are the same, whether you're at 0 miles an hour or 100 miles an hour. Therefore, what form number 2 is saying, it's saying, therefore, all experiments are going to work out the same. You could say to yourself, I'm going to do an experiment, because I know what would happen if I were standing parked in a parking lot. What would happen is the object would land directly below my hands. But what form number 1 is saying is, yeah, that's true. But that's also what would happen if you were going 100 miles an hour. And you know that, and your stomach knows that. That's why, like you know that intuitively already, because any minor little bodily experiments you ever do at 100 miles an hour always work out the same. Any physical experiment you would do, such as dropping an object or getting out a stopwatch and a ruler or a freaking laser or photo gate or any fancy dancy modern equipment that you could get, is going to yield the same results at 100 miles an hour as it would at 0 miles an hour, or as Caroline's pointing out, to the left or to the right or whatever, because the laws are the same. So form number 2 is saying, if you accept form number 1, if you accept what seems self-evident, that the laws are the same at all velocities, then that means there's no experiment you could do at any velocity to resolve what the velocity is. So that means, so I'm going to go on now. I'm thinking maybe that's a little bit clear. I'm looking at the time. So that means then form number 3 follows from form number 2. That means, since we are scientists now, so this now also goes back to what I think it was Sam or someone was saying before about good and bad. Was it Sam? I can't remember. Sorry. I just want to give credit where credit is due. Was it Sam? Sorry. Where did it go? Yeah. Going back to the Sam thing about like you can't know good without bad, I'm saying now, yes, if you've ever vaguely thought that in your mind and sort of emotionally thought there might be some weight to it, A, you're right. But B, I'm saying there's now actual scientific weight to it. I'm saying that you can't do an, I'm saying you can't do an experiment to figure out anything but a comparative velocity. You could figure out your velocity compared to the clouds, or you can figure out the cloud's velocity compared to you. Oh, that you can detect, you can see, you can do. You can figure out the elevator's velocity compared to the 4th floor, or the 4th floor's velocity compared to the elevator. You could compare the elevator to the earth, or you could compare the earth to the elevator. But as to what either one is doing in its own frame of reference, to go back to the SAM language, you can't do an experiment. You can't even think of an experiment to resolve that. And it's not because technology hasn't gotten advanced enough. It doesn't matter how advanced technology ever gets. The laws are the laws are the laws. And since the only thing we believe in science or physics is what we get from experiment, like this is why it's ultimately science, not just math, which I love math, not just philosophy. I love philosophy, not religion. I love religion. And I'm not being sarcastic. Like there's all these different ways to think in life that are all super, super important. But and I love them all. But what makes science specifically science is that it ultimately rests on experimental results for its notion of truth. And what form number 1 says is the laws of the laws of the laws. Duh. Form number 2 says, well, then experiments aren't ever going to show an actual absolute single velocity of a single object. And then form number 3 now says, well, if experiments aren't going to show it, and experiments are all we are our judge and jury and executioner in physics, then form number 3 says, and I'm writing it slightly differently from the way I wrote last time, but what it says in physics, and I know we only have 5 minutes, so I'm gonna get to the last equation, or I'm gonna get to one of those two equations now, finally, for the first time. I'm saying now that we are literally saying in physics from here on in, velocity is hugely important in physics. It's huge. It's so important that I have to spend weeks and weeks and weeks talking about velocity from all these different perspectives. Average speed, velocity, average velocity, average speed, instantaneous velocity, which I'm going to get to next. And now I'm saying also, if you're going to distinguish between absolute velocity and relative velocity, what I'm saying now is, oh, velocity totally matters in physics. Oh, velocity is totally real. Oh, velocity numbers totally are gotten from experiments and must be getting from experiments, and they mean something. But the only kind of velocity numbers from here on in that mean anything in physics, the only kind of velocity measurements we could ever get from the lab, from experiment, the only ones that ever mean anything in reality are comparisons. That from here on in, velocity is always and only a comparison, a relation of one object to another. And again, this goes back. I love Caroline's question about, is direction part of all of what I'm saying? Yes. Every time I use the word, and this is why we had to like drum it in the first couple of weeks. From here on in, anytime I say anything about velocity, I mean speed and direction. Together, that's the package of velocity that I'm talking about, speed and direction. But what I'm also now saying from here on in for the rest of physics is, whenever we talk about the speed or direction of something, it must be in relation to something else. There's no meaning to the speed or direction of any one thing in its own reference frame. So that was like Caroline's language and now Sam's language. Like, nothing has a velocity in its own reference frame other than zero. Everything is still compared to itself. Things are only moving at any kind of number compared to something else. And when you change what you're comparing it to, you change the number. So so that's, I'm literally saying form number 3 is saying from now on, all velocities are relative. From now on, so I'm going to give you form number 4, and we'll stop there for today. So each one of these forms is just another implication or another restatement of the same idea. We're just taking the original idea of form number 1, saying the laws are the laws, which again, I'm saying should seem self-evident. It's like, should seem very hard to argue. The laws are the laws. But if you really think about the fact that the laws are the laws, it means, well, then I guess velocity is a relation, not a property. And that means from now on that whenever we write velocity, so whenever I write V from now on with an arrow over it, I mean velocity as a vector. I mean velocity, speed, and direction, the Caroline point. And I'm saying, from now on, if I ever write a velocity vector, I must, or generally speaking, unless it's 100% clear what I'm talking about, from now on, I have to write velocity of one object relative to another. Velocity. Sorry, I know it's about to be. From now on, when I write velocities, I'm looking at the time, I know we have 2 minutes. Okay. If I write velocity subscript A, B, I mean the velocity of A relative to B. I mean the velocity of A in the reference frame of B, meaning the velocity of A if B is assumed to be still. Assumed, like hypothetically, like for the moment, like not like it actually is, because nothing actually is. But if B assumes itself to be at rest, assumed to be stationary, then it looks at A and measures A velocity. That's what we know as the velocity of A relative to B. And the last thing I'm going to say about this, the last form, so this is all saying velocity is relative, and I can go back to the page in a second if you want. But if you ever want to know the velocity of one object relative to another, but you don't know it. One thing to know, form number 4 is that velocities add, velocities add in this way. Now, what do I mean? I'll just write this really quick. Consider subways or escalators or luggage ramps. What I'm saying here very quickly, and I know it's, I think it's 1:30. I'm looking. Yeah, I just VAC equals VAB plus VBC. We'll pick up on this next time. But in short, what I'm just saying is, if you, you know, those moving ramps, if you're in an airport, you're on a ramp and you're holding your luggage, right? Or they're just like escalators, whatever. If you know, even if you've never thought about it mathematically, the velocity of u relative to the ramp plus the velocity of the ramp relative to the airport equals the velocity of u relative to the airport, right? Or better, velocity of u relative to a subway plus velocity of subway relative to New York City streets equals u relative to New York City streets. That's why you ride subways, because you can sit in the subway doing nothing and get somewhere. Velocities add in this fashion, but they add through different reference frames. Right. And you know, if you walk along the subway at 1 mile an hour relative to the subway, and the subway is going, or you walk on an escalator, you pass people, right? If you're going 1 mile an hour relative to the escalator, and the escalator is going 30 miles an hour relative to the Columbus Circle Mall, then you're going 31 miles an hour relative to the Columbus Mall. You've always known that. Everybody in this room, and it works if you go backwards and throw in negative signs as well. Everybody in this room has always known that intuitively. I'm telling you that it's actually a mathematical scientific truth that actually means something about the character of velocities. We'll end there. Sorry, I went over 1 minute over. I'll hang out if there's any questions, but you guys have been great, great, great. Thank you so much. Oh, yeah. So I'm here, but goodbye, but thank you so much and goodbye. And thank you. And I'll post the notes and blah, 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 blah.
Can you go back to the last page for a second?
Good question, Felicia. What happened to your avatar?
Thank you, Professor. See you tomorrow.
No, thank you. Sorry. And sorry. Yes, thank you. Wait, I'm stopping the recording too. Where's your avatar? Okay, I'm stopping.